Welcome to Chemical Reaction Engineering Laboratory. In past 3 weeks, we have done 3 experiments. One is ideal batch reactor, ideal CSTR and ideal plug flow reactor. So this is the 4th experiment we are going to perform and demonstrate to you all today. Today we are going to perform Cascade C.S.T.R. that is CSTR in series. So we have 3 CSTRs of equal volume. They are in series. So from one volume of the CSTR, the product will be sent as the feed to the second CSTR. From second CSTR, it will be sent to the third CSTR. Okay. Aim of this experiment is to study the performance of a saponification of ethyl acetate with NaOH in a cascade reactor system of CSTR, wherein we have 3 equal volume of CSTRs in series. And we will prepare a performance chart or a table where we compare the performance, that is what is the conversion in each reactor. So we will be preparing the performance chart for this reaction system, and we will determine the reaction rate constant at the ambient conditions, that is at room temperature. Okay. Well, coming to the theory part of this Cascade C.S.T.R. reactor, let us start with what is a cascade. Have you heard this word anywhere else? Actually, in fashion dress stitching, they call the word cascade. And if you go to a waterfall, we call it a cascade. Okay, what is a cascade? Actually, a small waterfall, typically one of several that falls in stages down a steep rocky slope. Okay, that is one from one rock, water will be falling down. Then it will be flat. Then again through another rock, it will be falling down. So that way it is called as a cascade. That is the output of one is the input to the next. Okay, that way it is coming as cascade. Same way in dresses also, fabrics, some circles and semicircles are cut from the fabric and is draped in different ways of the dress form, and the name is called as cascade because the fall of the drape is similar to that of a series of waterfall. It even forms beautiful cone shaped dresses. Okay, so that way we have cascade word is being used. Even in chemical engineering context, a cascade is a plant consisting of several similar stages, with each processing the output from the previous stage. Mostly these cascades are commonly used in isotope separation, distillation operation, flotations, separation and purification process, and even in reactors like CSTR reactors. Okay, in general, a cascade process is any process that takes place in a number of steps, usually because the single step is inefficient to produce the desired product. Okay. So if you consider the CSTR reactors, the reactants on entering the reactor are perfectly well mixed, and the contents of the reactor and the reaction products will be leaving the CSTR as a single stream. And if a CSTR can be either operated at steady state flow type, or even it can be used as a semi-batch type reactor. So actually, if we have more than one CSTR arranged in series, they can be used to perform the experiments. So that way we use the term cascade to indicate that the product stream of this one of the first CSTR will be the feed stream to the second CSTR, and the product stream of the second CSTR will be the feed for the third CSTR. Okay, so the final product stream is coming out of the third reactor. The conditions in one of the reactor in series are not influenced by what happens in the reactor downstream, but in other way they are influenced by what is happening in the previous reactor or the reactor which is upstream to the particular reactor. So we can even have n number of series CSTR arranged in series. When the n is tending to infinity, the performance will be equivalent to that of a plug flow reactor. Okay, that's why even we have a mathematical modeling. When you learn, you will be studying CS tank in series model, which will be when n tends to infinity, we have plug flow reactor. When n tends to 0, we are having a CSTR reactor. Okay, so we know the performance equation of plug flow reactor as well as CSTR reactor, right? With that we can explain what is the usefulness or what is the advantage of using such cascade type of reactors. Okay, for example, if you consider a plug flow reactor, we know the performance equation is tau by Ca naught equal to integral dxa by minus Ra, where the integration limit is from xa1 to xa2. Okay, similarly for CSTR we know that tau by Ca naught equal to xa1 minus xa2 by 1 minus Ra. Okay, so what happens is, for plug flow reactors we know that the volume of the reactor required is area under the curve, whereas for the CSTR reactors volume of the reactor required is the. Okay, this is where we are going to discuss about what will be the advantage if we have CSTR arranged in series. Okay, let us see that one. Okay, so for that we should be able to construct the Levensspiel inverse rate plot, that is 1 by minus Ra versus Xa plot. Okay, 1 by minus Ra versus Xa plot we have. So in this diagram you can see that in the left hand side we have a Levensspiel inverse plot where we have one CSTR, and in the right hand side for the same 1 by minus Ra versus Xa plot we have made two reactors. Okay, the first one is operating at a conversion of 55%, that is 0.55. So you can see the area, what is the total area when you use single CSTR and double CSTR. Okay, so in the left hand plot what we see is the construction of one CSTR with a conversion of 80% conversion, and if you consider the area of the rectangle is tau by Ca naught, which is equal to coming around 4. And if we compare the right hand side diagram where we have two number of equal volume CSTR in series with the conversion in the first reactor 55%, then final one it is 80%, you can see what is the area of each two rectangles is the same, and you can see the total area is 2.47. so first diagram or first single CSTR when we are using, the area is 4. When you use the two CSTRs, the total area is 2.47. so thereby what we have is around 62% of volume of the single CSTR is required when we use two CSTR of equal volume in series. What we can say again, I repeat, when the same flow rate, see remember for when you use single CSTR and when you use two CSTRs, the flow rates are kept constant. Okay, so in that case for equal flow rates the total volume of the two CSTRs in series is, if you compare the percentage, 2.47 is the area divided by 4 is the area in the single CSTR, which is coming around 0.62. okay, that is 62% of volume of the single CSTR is required when we use two CSTRs of equal sizes, and this is because the first CSTR is operating at a low conversion and higher rate than the second CSTR in series, which is operating at the same conversion as the single CSTR, and CSTRs in series is used fairly commonly to reduce the volume requirement, total volume requirement, while it will retain the same advantages that we get over the CSTR over a plug flow reactor. Okay, so when you increase the number in series, no, the total volume required will automatically decrease. That's what we understand from the plot. You refer to the plot here. When you keep increasing the thing, we tends towards, that's what means when n tends to infinity, it almost comes like area under the curve instead of rectangle. That is the what we understand here. Okay, when you use single CSTR it is a big rectangle. When you use two CSTR we have two rectangles of equal size, and we keep on increasing the number of reactor CSTRs of equal volume. What happens is we almost from the rectangular shape, the rectangle when you use infinity number of CSTR is, it is almost coming like area under the curve, which is almost equivalent to the performance of a plug flow reactor. Okay, so that is the advantage when you fairly increasing the number of CSTRs, then we are getting a conversion or a volume required is equivalent to that of a plug flow reactor. Okay, so what is the advantage? This will tend to decrease the cost, but however the reactor fabrication and the plumbing cost will tend to increase the other cost. Okay, because there should be some optimization. So it's a very good challenge for optimization people. Okay, those who want to do optimization problem, you can make a trade-off between how many number of, when you keep decreasing the volume of the reactor cost, Other end, we are fabrication cost and the plumbing cost is increasing. So there should be a trade-off between these two. Okay. And the plots shown are for kinetics where the rate is increasing with the reactant concentration. That is inverse rate increases with conversion that we know. For any such kinetics, the total volume of CSTRs in series will be less than that of a single CSTR. But however, remember, it depends upon the order of the reaction, right? For a kinetics which is having regions that are negative order, where PFR would have a larger volume than a CSTR, then CSTRs in series can have a larger total volume than a single CSTR. That also we should be careful. So positive orders, with increase in number of reactors, we require less volume. Whereas if the negative reaction order is there, in those cases where the plug flow reactor having a larger volume than a CSTR, obviously when you increase the number of tanks in series, obviously the total volume will be required will be more than the single CSTR volume. Okay, so we can see from the plots that as the number of CSTRs in series becomes very large, the total volume will approach the volume of single PFR. This will be true for any rate equations which are positive or negative order kinetics. Okay, that's why we have packed bed reactors and other tubular flow reactors that do not have a perfect plug flow can be modeled using this type of CSTRs in series. What we are not trying to do any modeling any perfect plug flow. We don't need an infinite number of CSTRs. Okay, axial dispersion is a combination of all processes that spread molecules out along the axis of flow that would otherwise stay together in plug flow. That is diffusion, turbulent eddies, flow between catalyst particles, etc. So the fewer CSTRs in the model, the larger the dispersion that is stimulated. Okay. So we should know that it is economically beneficial to operate several CSTRs in series or in parallel. This allows, for example, first CSTR to operate at a higher reagent concentration and therefore a higher reaction rate. So the apparatus is already I have explained you this apparatus in CSTR experiment number 2 itself. Now I will explain you what is this system. So we have a cascade reactor, we have a control panel where we have these 3 stirrers is required, right? So we have 3 stirrers connected to this system. So we have 3 stirrers are there and we have 3 main switch and stirrer switches are there. Okay, so what we have is a CSTR means a cylindrical volume, all are equal volume. So a cylindrical column with the bottom we have a valve to discard the solutions and we have a output stream or exit stream. Okay, where we have some sensors also. Okay, then we have 2 inlet section because we are doing saponification reaction. Reactant A and reactant B are ethyl acetate and NaOH. Okay, so we have NaOH being pumped through a pump and we have a feed tank A where we have 0.1 normal NaOH solution and another tank we have 0.1 normal ethyl acetate which is pumped through pump B. So through these tubes and this setup, this feed will be entering into the CSTR continuously. When we fix the RPM, we will have a continuous flow of reactants into the system. Then we have stirrer 1, stirrer 2 and stirrer 3. So we will be keeping a particular speed at which these stirrers are being operated. Okay, so then once the steady state is attained, so what will happen, once the level come to here, the fluid will flow into the second reactor. Same thing happen in the second reactor, it will get filled up to here, then the product stream will leave into the third reactor as the feed. So here the exit stream, the product stream from the reactor 1 is sent as the feed to the second reactor and the product stream from the second reactor is sent as the feed to the third reactor. Okay, so we have exit at the third reactor. This is the experimental setup where we have 3 cylindrical columns with bottom we have 3 valves for discarding the solution or collecting the samples. In this demonstration video, we are showing you only collecting sample from the third reactor alone. Actually, when we are performing the experiment, for every flow rate that we are fixing, we have to collect 10 ml sample from each reactor, that is reactor 1, reactor 2 and reactor 3. So keep this in mind while doing calculations. And we have 3 exit streams where the feed from the tank, product from the tank 1 will go as the feed to the second, and the product from the second tank will go as feed to the third tank, and we will be collecting the product stream from the third reactor. Okay, so as we have shown you in the previous laboratory, there are two feed tanks here. So we have feed tank A and feed tank B, where we fill NaOH and ethyl acetate in 0.1 normal solutions. Okay, so this is all about the experimental setup. The chemicals required will be explained by Miss Veena.
Required chemicals for Cascade C.S.T.R. 0.1 normal sodium hydroxide and 0.1 normal ethyl acetate 20 liters and 0.1 normal HCl and 0.05 normal NaOH. We have to standardize it with oxalic acid. Glassware required, burette, funnel, 3 conical flask, measuring jars, and one is HCl and one is 0.05 NaOH. Both. Phenolphthalein indicator and stopwatch.
So before starting the experiment, take in this beaker 0.05 normal NaOH and HCl is taken in a beaker, so that easily you can fill it in the burette. So 0.05 normal NaOH is filled in the burette up to 0 level and kept in the burette stand. So this we are doing so that immediately we collect the sample and we can perform the titration. Okay. So once we do that, what we will do is we will take conical flask and we take 20 ml of HCl and add it into 3 conical flasks respectively, 20 ml in each. We are adding 20 ml of HCl into the 3 conical flasks, 1, 2 and 3. So we will do 3 readings at 3 rpm. So if you do at 5 rpm, we will take 5 conical flasks. Okay, and we will add 2 drops of phenolphthalein indicator to each of these conical flask. Drop 1, drop 2, drop 1, drop 2. Okay, so now we have this ready. Take this stopwatch. We will go to cascade reactor apparatus with this measuring jar to collect 10 ml of sample after steady state. Okay. So we can switch on the pump. We have checked whether the tank is filled with this, right? We can switch on the motor and we can switch on the stirrer also. Okay, so we have to switch on all the 3 CSTR stirrers also. So for that we will switch on this. Keep same speed in all the 3 at the same RPM. We have to keep same speed, 30 speed. This is giving 30%, 30% and 30%. Whatever it is, it should be same for all the CSTRs. Remember last time we did only one CSTR. We have to ensure that this is rotating. Yeah, all CSTR stirrers are working. So once we have done that, we already switched on the main switch. So now we can switch on the peristatic pump and keep 60 rpm in both. Set the value to 60 rpm. Okay, so even in the beginning if it is in different rpm, we have to ensure that first reading we do at same rpm. So in both peristatic pump we are keeping 60 rpm and we start the stopwatch. This is only to ensure how much time it is taking for steady state to attain. Okay, as you see, any air bubbles are there, we have to check. Okay, it will take certain time for the fluid to enter into the tank. Wait for some time. We are keeping all the 3 CSTR. So the difference between earlier experiment and this experiment is, here we are letting the product mixture from the reactor 1 to enter as a feed to reactor 2. Again well mixing is taking place. CSTR reactor, complete back mixing is there, and we have the product stream from the reactor 2 which sent us the feed to reactor 3. Okay, where again we maintain the continuous stirring and back mixing, complete back mixing, ideal CSTR in series, 3 CSTRs. It is called as cascade reactor. Here what we are doing is we are trying to increase the conversion, because in first reactor certain percentage of conversion taken place, and we are continuing the reaction in another reactor where another time is there. Okay, so that way we are trying to increase the conversion. We have to ensure that we don't let it go down. So third CSTR, there is no fluid till now. Second CSTR is empty. Third CSTR, almost 50% of the fluid has come. Actually, in regular laboratory, you can do even as low as 10 RPM, 8 RPM like that. Okay, so now we are doing higher speed so that we can save the time. So keep checking that if there's any blockage is there, we should be able to identify. So it may take around 5 to 10 minutes. After that, what we will do? We'll collect 10 ml of sample from this product stream from the third reactor. Okay, so we have to wait for that. First this reactor has to get filled, second reactor has to get filled, and third reactor has to get filled. Okay. So what we are doing is only we are collecting the sample from the third reactor, but as an additional exercise, if when you are performing the experiment, we can collect sample from all the three reactors after that certain time steady state and see what is the conversion in each reactor also. Okay. So we will be doing 3 titration in that case when you want to know intermediate conversion at reactor 1, reactor 2 and reactor 3. So now what we are doing is overall conversion at the end of the third reactor only we are determining in this simple laboratory experiment. Okay. So what we can see is that the first reactor has got filled up to that baffle level, outlet stream level. So you can see even the second tank is also got filled up to this level. So we have product being getting into the third reactor as well. Okay, so third reactor we are having certain level filled with the water, the reaction mixture, right? So it means that we have up to this level water has filled, the product stream has filled. So once it comes here, after that we will wait for 5 minutes to collect the sample and do the titration again. So it's here. Okay. So it may take another 5 minutes. So it just took around 7 minutes. You could be able to see 2 tanks got filled. What we are doing, we have kept the peristaltic pumps at 60 RPM and we kept equal speed for all the 3 stirrers. Stirrer 1 connected to CSTR 1, stirrer 2 connected to CSTR 2 and stirrer 3 connected to CSTR 3. So we have water up to this level. Another 1 centimeter height rise, we are going to have outlet stream. We are going to witness product being coming out of the reactor 3. Okay. Yes, we can see the product stream start coming. So now we have to note the time, and within another 5 minutes we wait for steady state time. Okay, so we will collect 10 ml of sample from this after another 5 minutes. What is the setup here? This funnel collects the water and discards it into the sewage collection. Remember, these chemicals has to be discarded with the proper precautions. Okay, so we have the product stream coming out of the third reactor. Okay, so now what we can do, we can take the measuring jar. We waited for 5 minutes, so it took 10 minutes exactly for this particular RPM of 60 RPM to get it. According to your RPM, the time taken for the product stream is come out will be different. Okay, we are collecting the sample. So what we will do, we will collect 10 ml of sample. Okay, so once we collect this 10 ml of sample, what we will do, we will titrate it against. Well, before starting the titration, what you have to do, we will switch off the pump to save the chemicals. Okay, we will switch off the flow rate, and we have to empty the tanks before we do the second experiment. That we will do later. Switch off the main switches also. Okay, so now we have taken 10 ml of sample and we are adding it to 20 ml of HCl solution. We added 2 drops of naphthalene indicator. Now 0 level is there. We are going to titrate. Slowly add after this. So appearance of permanent pale pink color is the end point. So now we have the permanent pale pink color. You can add one more drop. Okay, please note down the reading, volume of NaOH consumed. Okay, so now we'll take the measuring jar and we'll go for second set of reading. So now for the second set of reading, we will again switch on the mains. We are keeping not changing the speed of the agitator because we want to maintain the same. Switch on the peristaltic pump 1 and 2. Earlier we had 60 RPM. Now we will keep it to 70 RPM in both the peristaltic pumps. That means feed rate is changed to 70 RPM. Okay, and start the stopwatch. And we will just wait for another, because if higher the speed, last time it took 10 minutes. We may be getting the steady state after within 7 to 8 minutes. That means what? Again, so from the fresh tank 1 has to get filled. Similarly, tank 2 has to get filled and tank 3 has to get filled. Then only we will have the flow rate of the reactor. Okay. So same way, before starting, we have to ensure that both tanks have sufficient amount of NaOH to perform the reactor. Okay. Otherwise we have to refill the tank. Okay, once you refill only, we have to switch on the motor and keep the RPM to 70 RPM. So we will wait for another 8 to 9 minutes for the liquid to flow from the tanks. Okay, we have to remember, after emptying the tanks, we have to close the valves. Okay, now here also we have to keep the tank closed. Then only water level will increase, right? So we waited for 10 minutes. So once the product starts coming out, we will start collecting the sample from the reactor 3. Okay. The water level has come around 60% in the tank hole. You can see that. So we will wait for time for water to flow out of the third reactor. So waited for time. You can see we have the continuous outlet. We waited for some time. You can see the level of liquid in all the 3 tanks are up to the outlet pipeline level. Now we will collect 10 ml of sample corresponding to 70 rpm. Okay, so what we do, we collect 10 ml of sample. If excess is there, we will remove it, and before that we will switch off the motors. Okay, and we will titrate it against NaOH solution. So this is the second one corresponding to 70 rpm. Refill the NaOH in the burette. So take the second conical flask and titrate it against NaOH. What is this? 10 ml of sample corresponding to 70 rpm, and we have added 20 ml of HCl and 2 drops of phenolphthalein indicator, and we are titrating it against NaOH solution. That is 0.05 normal NaOH solution. We have to note down the end point. So stop it exactly when you get the end point, permanent pale pink color appearance. Okay, so please note down the end point. Now we will go to perform the third set of readings. So before that we have to empty the tanks, empty the reactor 1, 2 and 3. So open the valves at the bottom of the reactor 1, 2 and 3, and we will have, we are emptying the tanks 1, 2 and 3. So after emptying the tanks, what we will do, we will close the valves at the bottom and we will switch on. We have to ensure that the collection tank is having sufficient NaOH and this. Okay, so if not, we have to refill the tank. For 3 readings we need to ensure that. Okay, so now we can switch on the motor and the agitators, and we will change the RPM to 80 RPM for third set of readings, and we will wait for 10 minutes for the steady state to attain. Okay, start the stopwatch and note down how much time it takes, and wait for the product stream to come out of the third reactor. Okay, we can see the first reactor has filled and the second reactor is half filled. So once it is filled up to this level, we are going to have feed to the third reactor. Okay, what is it? We are doing it for third time at third RPM, that is 80 RPM. We started with 60 RPM, 70 RPM, and now we are doing for 80 RPM. Okay, so the flow of fluid from the third reactor started coming out. We waited for 5 minutes. Okay, so after time, waiting for 5 minutes, we collect the sample of 10 ml. Okay, and switch off the motors and empty the tanks before starting the titration. Okay, so we will discard all the chemicals. Now we will do titration against NaOH. So add this to 10 ml of sample to 20 ml of HCl and 2 drops of phenolphthalein indicator. Titrate it against 0.05 normal NaOH solution. Okay, so we have filled it to 0 level. Start the titration. So you can see the difference. This week we got the perfect endpoints. That's what with practice we'll be able to get the exact endpoint. You note down the endpoint. So we got 3 titrations. Okay. And before moving on to calculation part, what we have to do, we have to empty the tanks also. So feed tanks A and B should be emptied before we leave the lab. Okay, so this feed tank A and B needs to be collected. NaOH is collected in that. You are discarding, So we have emptied the tank. Okay, so we have to ensure the tank is empty. If possible, we have to rinse it with water. Okay. So the chemical smell will be there. So wear mask. Okay. So once then switch off the main switch. Now we will see the observation and calculation part. Well, coming to observations and calculations part, so preliminary titration, we have to repeat what we have done in our batch reactor and all the experiments. First step is to standardization of NaOH using oxalic acid, and then standardization of HCl using NaOH. Okay, so from that we will estimate the exact normality of NaOH and HCl solutions. Coming to this particular experiment, observations are, so we have done experiments for 3 RPMs, 60 RPM, 70 RPM and 80 RPM. So we have three different flow rates. For each flow rate we have determined we have collected 10 ml sample from reactor 1, reactor 2 and reactor 3, and we have endpoints. We titrating it against 0.05 normal NaOH. We have 3 endpoints, that is corresponding to reactor 1, reactor 2 and reactor 3. Okay, similarly for second flow rate 70 rpm, again we will have 3 endpoints for the 10 ml samples collected from reactor 1, reactor 2 and reactor 3 and titrated against 0.05 normal NaOH. Similarly for third flow rate 80 rpm, again we have 3 endpoints, that is the amount of NaOH consumed, volume of NaOH consumed for the reactor 1, reactor 2 and reactor 3 samples taken. Okay, in the demonstration video we showed you only reactor 3 sample collection and titration, but similar titration has to be done for the 10 ml sample collected from reactor 1 and reactor 2 also. So those 3 endpoints needs to be noted down. From that it is easy for us to go for the calculations. Okay, so calculation part will be explained now. So coming to this calculation parts, so we know the how to determine the total volumetric flow rate, because in liters per hour we have flow rate of A and B, where A is NaOH and B is ethyl acetate. Those two are our reactants for our saponification reaction. Okay, so by combining these two FA plus FB values, see, remember we are noting down only RPM values. From RPM value it is easy to determine what is the liters per hour value, because the conversion fraction is given in the observation part. Okay, so you can calculate the total volumetric flow rate V naught. Okay, that is small v naught, and we know the definition of space time, it is V by V naught, where capital V is the volume of the CSTR reactor. Again, volume of the CSTR reactor is same for all the 3 reactors, and the value is known in the given observation. Okay, around 0.96 or 0.97 liters. Okay, so we are going to get space time value from that, and we have to know we got the endpoint, that is the volume of NaOH consumed during the titration is a V3 value, titer value. So from that it is easy for us to calculate what is the concentration of NaOH. Okay, so Ca value can be determined using the formula V1 N1 minus V3 N3 whole bracket divided by V2. So this will be in gram moles per liter. So that is the concentration of NaOH in the product stream. Okay, so same value we can determine for reactor 1, reactor 2 and reactor 3. So once you know the concentration value, we know what is the initial concentration, right? Ca0 value we know. So from that we will be able to get the conversion data also. Conversion in the first reactor, conversion in the second reactor and conversion in the third reactor can be determined. Okay, so because here we have 3 CSTR connected in series. So whatever is the XA3 value, that is a conversion from the third reactor, is the overall conversion of the 3 CSTRs connected in the series. Okay, we know what is the formula for conversion, right? XA equal to 1 minus CA by CA0. Okay, and CA0 value also we can calculate from the what is the normality of the feed tank, right? If both are 0.1 normally each, so easy to find out what is we know the flow rates, FA value, FB value we know. So from that you can calculate what is CA0 value. Okay, so from that you can easily get the XA value, and even the rate constant value calculated assuming second order reaction, you can get the K value for the particular reaction, particular set of samples. You can do calculate the rate constant. So for each reactor we are going to have a rate constant, reactor 1, reactor 2 and reactor 3, and from that we will be able to calculate what is the average rate constant for a given flow rate. Okay, and calculation table will be made with the CSTR1, CSTR2 and CSTR3 for a given particular flow rate. We will calculate for titration value is known, concentration value is known, conversion value is known, K value is determined and average K value is calculated. Okay, the same procedure has to be repeated for flow rates 2 and flow rate 3, that is for 70 rpm and 80 rpm. Okay, next we will move on to results and discussion session. So in this section we have to report the result that we obtain and we should able to give the inferences that we observe. Okay, so the rate constant for the given reaction is the average of K1, K2 and K3, which is so and so liters per mole minute inverse. Okay, the performance chart for the Cascade C.S.T.R can be made in the following table. Okay, so we have flow rate for a given flow rate, what is the tau value, what is the conversion in reactor 1, conversion in reactor 2 and conversion in reactor 3. So that can be summarized in this table, and inference whatever you have observed can be written. Okay, we will observe that the conversion is increasing or not, what with increase in volumetric flow rate, what is the change in conversion, all that can be written. Okay, okay, next moving on to the readings for practice. So we have given you a table where we have given volume flow rate of A and B. Both are kept as 160 rpm. So that is the first rpm, and then from the titration value you will able to calculate the concentration value. Okay, so then you will make a calculation table where you will calculate up to XA value and then K value also. Okay, so once you calculate the XA value and K value for the CSTR 1, 2 and 3 for a given flow rate, average of the K value has to be determined. Okay, so the same calculation and calculation table needs to be made for all the 3 flow rates. I hope you will be able to complete that part. Okay. In this fourth week of chemical reaction engineering laboratory, we have demonstrated you Cascade C.S.T.R, where we have performed the experiment and determined the rate constant. We have determined the value of the reaction rate constant on the basis of Cascade C.S.T.R flow model for the saponification of ethyl acetate in the CSTR flow assembly, and we have studied the performance of PFR in terms of conversion of reactants with respect to varying the reactor volume and feed flow rates. We sincerely acknowledge the contributions of Dr. Vidyasagar, Dr. Manogar and Dr. Ramya for the infrastructure development in this CRE laboratory, and we also thank our previous HODs, Professor Sarath Babu, Professor Sirishwanavani and our current HOD, Dr. Srinath. Thank you so much for joining my classroom. Meet you in the next video.